A spectrum is a sequence of pointed spaces, x sub n, where n is greater than or equal to 0, and this comes equipped with maps from the suspension of x to xn plus 1, and this map is adjoint to a map like this. And I'm going to call this map epsilon upper x sub n, and this will be eta upper x sub n. Okay, and a map between spectra is what you think it is. Now, how might you, there's various ways you might generalize this. One, instead of talking about a sequence of pointed spaces, they could be a sequence of objects in your favorite model category. Or another thing you could try is you've got this pair of adjoint functors. They form a Quillen pair. That means suspension plays nicely with cofibrations and loops plays nicely with fibrations. So you might replace this pair of functors by some other Quillen endopair on your model category M. Now, Hovey has written a couple of papers about this kind of generalization, but I'm not going to pursue that. What I'm going to do instead is reformulate this in terms of enriched category theory, so that I'll be able to say a functor is a spectrum. I'm sorry, a spectrum is a functor from a certain indexing category to the category of pointed topological spaces. And I won't have to say anything about these structure maps because that will be built into the functor. So this uses enriched category theory. Now, in enriched category theory, in ordinary category theory, you have objects and you have sets of morphisms. Between any two objects, there's a set of morphisms, and you can compose morphisms, and there's an identity morphism, and so on. In enriched category theory, instead of having a set of morphisms, you have a widget of morphisms, where a widget is an object in a fixed symmetric monoidal category. The category of sets is symmetric monoidal, but in enriched category theory, you replace sets by some other symmetric monoidal category or closed symmetric monoidal category. So, so a category. So this was invented by Eilenberg and Kelly in the late 60s. The category enriched over a closed symmetric monoidal category V has so let's say call C the category. So it has morphism objects in V, and this ground category V has to be monoidal, so you can talk about composition maps, composition morphisms. So, so let's say CXY is the widget of morphisms X to Y. So then what you need is you need to be able to do the following. So I'm going to give a name to this. I'm going to give a name to the binary operation in V. I'm going to use the tensor product sign. And so this tells you how to compose morphisms. Now, if it was an ordinary category, this would be a set, this would be another set, this would be Cartesian product, and you'd be taking a pair, so you'd have a morphism from X to Y and a morphism from Y to Z, and you compose them and you get a morphism from X to Z. Now, I am using the calculus convention here, meaning I'm going to write, when I want to compose functors, I'm going to write them the way we write them in calculus class. That is, the situation here is this, and the composite is known as GF. That's the calculus convention. So that's why this is on the left, and the map from Y to Z is on the left, and the map from X to Y is on the right. It's the opposite of how you see them in this diagram. Anyway, that's what an enriched category is. Now, I'm going to define a particular enriched category that is useful for redefining conventional spectrum. So, definition, J superscript n is the T category. Now, T means pointed topological spaces. So when I say a T category, I mean a category in which I have pointed spaces of morphisms rather than sets. Okay, it's a T category whose objects are natural numbers n, and then I have to tell you what the morphisms are. So I have to tell you what the morphism is. The morphism object from M to N, and it's the following. It's the sphere of dimension n minus m, provided that makes sense, and otherwise it's a point. Okay, so that's a category. And then I have to tell you how to compose morphisms in that category. So I have to give you a map. So what is this? So this is the sphere of dimension p minus n. Let's see, the appropriate binary operation is smash product, because these are pointed topological spaces. So the symmetric monoidal category is this. The category is T, the binary operation is pointed spaces. The binary operation is smash product, so the unit is the zero sphere. Anyway, this is S n minus m, and this is S p minus m, and there's a standard homeomorphism here. You smash this sphere with this sphere, you get this sphere, and there's a standard homeomorphism, and that's our composition morphism. So now, a spectrum is a T enriched functor from the small category I just defined, to the category of topological spaces. So if the name of the functor is x, then my convention is that the image of the element n here, I will denote by x sub n. And then the convenient thing about that is the structure map up there that usually defines a spectrum is built into this definition because it's part of functoriality. So, so in particular, we get automatically a map like this. This is built into the fact that it's a functor. And I'm going to call this subscripts here. So this is the structure map that we had before, or a generalization of it. And it's built into the fact that this is a functor. I don't have to say sequence of spaces with structure maps. All I have to say is functor from here to here, and the structure maps are built in. Now, here is a subtle point about this category. Jn, the category I just defined here, is monoidal under addition. So remember, there's an object for each natural number, and you can add natural numbers, and that gives you a monoidal structure on this. But it's not symmetric monoidal. Now, it took me a while to, I was puzzled by this when I first saw it. I thought, how can addition not be commutative? It's got to be symmetrical. But anyway, it isn't. I'm going to explain why. I learned this explanation from Peter May. So it goes like, so now I'm going to introduce my favorite new symbol. See that? That's a Japanese character. It's the character yo for Yoneda. And I'm going to put a superscript on it, or let's make it an n. So n is some element n is an element in our category. Now, this is a functor from our indexing category into T. Now, in general, the way you define the Yoneda functor is, let's say K. So it's a functor from here to here. So I'm supposed to get a sequence of spaces out of it. So the sequence of spaces I want is this one. So I've got an n here. And we know what this is. This is the sphere of dimension k minus n. And this is for k. Okay, so this is a functor from this is a spectrum. In fact, this defines a spectrum. You could think of it as the formal desuspension of the sphere spectrum. But anyway, this is a construction you can do whenever you're looking at whenever you have a category that's enriched over the category that you have a functor to, then you can make a definition like this. Now, Yoneda originally made this definition for, he had an ordinary category, and if you pick an object in your ordinary category, then you can consider the set of maps from your fixed object to any other object, and so you get a set-valued functor on the category that you're dealing with.
So Doug, you are talking covariant functor all the time.
Yes, this is a covariant functor, yes. N is fixed. Now, this guy right here, if you think of this as a functor in two variables, is certainly contravariant on this variable, but this variable is fixed for this discussion. Now, I'm interested in a particular case of this. I want to do this for n equals 0. So now we have a functor from j of n to t, commonly known as the sphere spectrum. So it sends n to Sn. Now, I'm going to use that functor to explain why this category is not symmetric monoidal. Now, if it were symmetric monoidal, then there would be an there's a functor that has to do with changing the order of the variable. So if j of n was symmetric, we would have the following. I'm going to just make sure I got this right. We'd have a map like this. And this is supposed to commute up to natural isomorphism, and this is, so this is the map that switches the two sets of coordinates. Now, in the world of topological spaces, we certainly have a map like this. However, the problem is that this interchange map is not in the image of the Yoneda functor. The reason for that, I may be dealing with the product of, probably dealing with the product of two copies of j of n. Symmetric monoidal means that there's a map like this that swaps the two factors, and then this diagram commutes up to isomorphism, up to natural isomorphism. Now, the problem here is that in our category, this guy, according to the definition, which is now hidden, this is S0, meaning it has 2 points. So what that means is that in this diagram here, there's only 2 maps from here to here that are in the image of the functor. One of them is the identity map, and the other one is the trivial map, the map that sends everything to a point. Those are the only, you've only got, this is 2 points. So there's only 2 maps in our category from an object to itself, so to speak, and they are the identity map and the trivial map. This map that swaps coordinates isn't in there. It's not part of the category. So the category is not symmetric monoidal. Now, this is one way of describing the difficulty with smash product that plagued our subject for decades. So let me explain. I want to explain now how wonderful life would be if this category was symmetric monoidal. So there's this wonderful construction called the Day convolution. And Day it's named after Brian Day, the Australian category theorist. So it goes like this. So let's suppose that, so he wrote it something like this. Let's say V is a closed symmetric monoidal category. And closed symmetric monoidal category. And J is a small symmetric monoidal category enriched over this given category V. Then we want to look at functors from J to V. Now the notation that's used for this by Kelly and others is this, square bracket J comma V. So this means the category of enriched functors. Okay, that category is closed symmetric monoidal. Now, just imagine, so the situation we're in, we've got our closed symmetric monoidal category T, pointed topological spaces, and we have this indexing category, this small category that is enriched over T and is monoidal, but not symmetric monoidal. Now, if it were symmetric monoidal, that would mean the category, the functor category, which in our case is the category of spectra, that would make the category of spectra closed symmetric monoidal. And so Adams wouldn't have had to spend 30 pages explaining why a very awkwardly defined smash product of spectra is associative up to homotopy and so forth. We would have a closed symmetric monoidal structure on the nodes. And notice, the word homotopy has not yet been written on the blackboard. This is not homotopy theory. This is category theory. You don't have to say that. It doesn't say symmetric monoidal up to homotopy. It's symmetric monoidal, period. There's no hedging here. Now, that is, but the hypothesis is, the hypotheses require both V and J to be symmetric monoidal. Now the J up here is not monoidal. Now, the proof of this, I'm going to indicate the proof. I don't know if this is, anyway, here's a one-line description of the proof. It's a diagram. So it goes like this. Okay, so I need notation for the operations. So let's say use the smash product symbol for the binary operation in V and S, which you should think of it as S0 for the unit. And in the other category, J, I'll use a plus sign, and I will call the unit 0. I'll use the symbol 0 for the unit. Okay, so now I'm going to tell you how to define the product of two functors. So it goes like this. So let x and y, v functors from J to V. Then you can consider J cross J mapping to V cross V by x cross y. And then in V, we have the smash product operation. And then in J, we have an addition operation. So we have a diagram like this. Now, what we're looking for is a map like that that has appropriate properties. And the construction that will do it perfectly is the left con extension. So I'm going to call this x smash y, and this is the left con extension. Now, left con extensions are always defined provided you've got a small categories here and a co-complete category here, a category that's closed under colimits. So I guess I should have said that in the hypotheses. Co-complete. So I left that out. V has to be co-complete. If it is co-complete, then this left con extension exists and it does exactly the right thing. It's exactly what you want. Okay, now let me repeat. In the classical spectrum situation, the problem is that our indexing category J sub n is not symmetric. So this theorem doesn't apply. So what do? We soup it up, we make it a little bigger so that it is symmetric. Now, this history, the first time anybody figured out how to make a stable homotopy category that was closed symmetric monoidal, this was originally due to EKMM. Their book appeared in 1997. I once asked Tony Elmendorf when they knew they had a closed symmetric monoidal structure, and he said June 12th, 1993. He remembered the day. Over 20 years later, he remembered the day. That was just a few days before Wiles announced his proof of Fermat's last theorem here. Okay, so here's what we're going to do. We want to replace this Jn that I've defined with another category that is symmetric monoidal. Now remember, the problem with Jn is that it didn't have enough internal maps. We needed some map inside Jn that would, when you apply some functor to it, you're supposed to get the map here that swaps coordinates. And we didn't have such a thing. That's why J upper n failed to be symmetric monoidal. So here's a new one. Well, I'm going to give you two of them, in fact. J sigma. What is J sigma? It has the same objects as before. Its objects are natural numbers. But now, and then this is going to be a pointed topological space. Now, previously it was simply a sphere of the appropriate dimension. Now, now it's going to be this. So previously, so this is assuming n is big enough. It's still a point if n is too small. Okay, now remember, in this category, the original category, the description was this. This morphism space was just a sphere. Now I'm going to take a wedge of spheres that is like this. So so sigma n here stands for the symmetric group on n letters. And for the purpose of this construction, you should think of say the K-sphere as the one-point compactification of RK rather than the textbook description, which is, the textbook description of SK is it's the unit vectors in RK plus 1. We don't want that. We want to think of it as the one-point compactification of RK. That means it has an action of the symmetric group sigma k by permuting the coordinates. So that's what's going on here. This symmetric group is acting on this sphere by permuting coordinates. And then I am taking the product, maybe I want to write it like this, I can't remember. I'm taking the product up with sigma n. So I'm getting, so this is a wedge of, this is a wedge of n factorial divided by n minus m factorial copies of this sphere. And the symmetric group is acting as indicated here. So that's my morphism object. Now, this means that I have the morphisms I need to make this work. So this category is symmetric monoidal. And so we can apply the Day convolution. And okay, so the functor category, so this is symmetric monoidal. So Bayes' theorem applies to the functor category J sigma into T, and this is known as the category of symmetric spectra. So I'll denote it like this. So, and this was studied by Hovey, Shipley, and Smith. So this was discovered sometime in the late 90s, and their paper appeared around 2000. For them, they used simplicial sets instead of, they use pointed simplicial sets instead of spaces. But I have my reasons for preferring to use pointed spaces rather than simplicial sets that I'll get into later. Anyway, so with this, so that means we've got, this is a closed symmetric monoidal category. The category of symmetric spectra is closed symmetric monoidal. So we finesse all the problems that plagued homotopy theorists for decades. Now, that's one way to do this. There's a second way to do this, and it has a similar setup, except we replace the symmetric group by the orthogonal group. So, so I'm going to define another category, JO. So this is an O, not a 0. And the set of morphisms here is we use the orthogonal group instead of the symmetric group. And so this also has the required maps that interchange coordinates. Of course, this gadget is a subspace this gadget. There's an obvious functor from here to here. And so that leads us to another category, the category of functors from JO to T, and this is the category of orthogonal spectra. Right. Okay, now, before proceeding further, I want to look at this. This is, so, okay, so this guy was, if you forget about the group action, it's simply, this thing was simply a wedge of so many copies of this sphere, a certain number of copies of this sphere. This gadget is a little more subtle, and I want to describe it in more details. So I call this the Mandel-May space because they were. So let OMN be the steeple manifold of orthogonal embeddings of Rm into Rn. Then, if you've got such an embedding, you get yourself a orthogonal complement. So if I call the embedding tau, tau. So such an embedding gives an orthogonal complement that the vector space of dimension n minus m. So you can use that to define a vector bundle over the Stiefel manifold. So the fiber at each point is this particular subspace of Rn. So you get a vector bundle over the Stiefel manifold. I see some puzzled looks. Do you want me to explain this? You have an orthogonal embedding of Rn into Rn. It has an orthogonal complement. Yes?
Can I just ask what you mean by orthogonal embedding?
An embedding that preserves the inner product. So it preserves the inner product. Each of these comes equipped with an inner product, the usual Euclidean inner product, and it preserves the inner product. An orthogonal embedding is supposed to preserve the inner product.
Why isn't that a map to the Grassmannian?
Well, there is a map to the Grassmannian, but there's more information here. Well, anyway, well, you know, there's a map from the Stiefel manifold to the Grassmannian, but when in the Stiefel manifold, you've got a, if you have a basis here, you get a basis. And, anyway, it's the Stiefel manifold, not the Grassmannian, that we want to use. So, for each such embedding, I get an orthogonal complement. So that's a certain subspace of the big vector space Rn. So, so I get an Rn minus M bundle over the Stiefel manifold, and I want to take its tome space. So it turns out that that's what JMN, that's what the J. It is the tome space. Turns out that JM, this Mandel-May space is the tome space. Yes?
Dumb question. How do you actually prove that that tome space is that description?
I'm not sure I remember how to do that, but it's not hard. I'm going to cop out. I don't remember it precisely, but you can do it. This is not a deep. There's nothing deep here. Now, so here's some examples. So first, let's consider the stupid case where n is less than m. Okay, in this case, there are no orthogonal embeddings. The embedding space is empty. We're looking at something over an empty space. Now, a tome space, by definition, always has a pointed infinity. So, so in this case, the Stiefel manifold is empty, but you still have the pointed infinity for your tome space. Okay, two. Let's suppose the two guys are equal. In that case, the Stiefel manifold is simply the orthogonal group. The orthogonal group. The bundle is, the fiber of this vector bundle is 0, because the orthogonal complement is 0. So now we're looking at a 0-dimensional bundle over the orthogonal group. Now remember, there's still a pointed infinity. So in this case, we get ON with a disjoint base point. This is the pointed infinity in the tome space. One more example. Let's say n is 1 more than m. Now, if I embed, so this is now an embedding of codimension 1. Okay, so what do I want to say? In this case, I claim that the Stiefel manifold is none other than the special orthogonal group of dimension m plus 1. And that's because if you have an embedding of Rm into Rm plus 1, you have a choice. You've chosen m orthonormal vectors in Rm plus 1. So the orthogonal complement is a one-dimensional subspace, and it has 2 unit vectors, and you pick the one that gives you the right orientation. And so you'll get this homeomorphism. And there's a line bundle over this. In this case, the vector bundle is a line bundle, and you can convince yourself that it's the trivial line bundle. And so the you get the suspension of SOM plus 1. Oh, here's a fourth example. Didn't want to forget. Let's suppose m equals 0. What happens then? You're going to have to answer this. What happens in the case m equals 0? What does the Stiefel manifold look like in this case? This is just like freshman calculus. What is the space of orthogonal embeddings of a zero-dimensional vector space into something? This is not a hard question. What is it?
Point.
What?
Point.
Yes, very good. It's a point. Yes. Okay, the Stiefel manifold is a point. Now, we have a vector bundle over this point. The fiber is Rn. And we're taking the tome space of that. So what do we get? Sm, yes. Okay. Okay, so again, let me remind you, this is a symmetric monoidal category, and the category of functors from it into pointed topological spaces is a closed symmetric monoidal category by Day's theorem, and it's known to us as the category of orthogonal spectra. Now, who did the homework? You know there was a homework assignment that was in a previous email, and the homework assignment was to read something in the introduction to the book. First, there's a quote from this. First, there's something that Adams wrote in the early 60s talking about the hare and the tortoise in homotopy theory. He didn't know it at the time, but the hare is Peter May. I don't think he and Peter had met at that point, but the hare is in fact Peter May. He couldn't have known that at the time. Anyway, I wrote, so in the book there's an imaginary letter from me to Frank written 50 years later, in which I'm explaining all of this, and then I say, okay, well, so this raises the following question. These orthogonal and symmetric spectra are wonderful things, but suppose you've got a spectrum that you know about, and it's only defined in the original way. How do you know that this has anything to do with orthogonal or symmetric spectra? In other words, how do you know that this wonderful closed symmetric monoidal category is going to deal with the problems, the examples that we're really interested in? That's a fair question, and fortunately, it has a very good answer. So the answer goes like this. So if I have a spectrum as originally defined, That's a functor from my original category into T. Okay, now, there's an inclusion functor of this into, say, the JO. There is an inclusion functor of JN into JO. Remember, these two categories have the same objects. Their objects are natural numbers. Here, the morphism set is a certain sphere, a sphere of an appropriate, the morphism object is a sphere of appropriate dimension. Here, it's this tome space. The sphere is sitting inside the tome space. In fact, you can think of this tome space as a wedge of spheres parametrized by the Stiefel manifold. You can think of it that way. Anyway, there is a straightforward functor from here to here. So we're looking for a functor like that, and again, the answer is left con extension. You can take any spectrum you want and convert it to an orthogonal spectrum by means of a left con extension. So all the stuff you wanted to do with spectra before, you can still do. And I've been thinking about this for a couple of years now. This is an amazing thing about stable homotopy theory. Every couple of decades, we change the foundations of the subject. We change the way we define spectra. And yet, we never have to redo any old calculations. Whatever things we calculated before, atom spectral sequence, algebraic K-theory, blah, blah, blah. We never have to go back and say, oh, with this new definition, we have to go redo these old calculations and check. We've never had to do that, never. Even though the foundations of the subject keep changing, the calculations we actually do with it seem to be unaffected by this. The next thing in my notes, I'm now halfway through the notes I wrote for today. I've been talking an hour. Maybe it's a good time to stop. But the next thing I have going equivariant. The next thing is to describe how to do all this when there's a G action involved. So I wanted to talk about logistics. I don't know how many talks you want to hear. I don't know if you want to hear more of this or if you want me to go in some other direction. But I do know this. My wife is coming for a 2-week visit a week from tomorrow, and I plan to disappear for those 2 weeks.
Maybe you click the button.
What? What should I do?
Do you still want it to be recorded?
Maybe not. Yeah, let's not record this. So how do I? Oh, stop.